Hello viewers of mine, this is a What the Physics video. This one is on vertical circles. Vertical circles is part of circular motion, but specifically we're going to be talking about just applications of circular motion. So as in we're going to be going like over hills, between hills, speed bumps. Just want you to see how it applies to real world scenarios. So vertical circles learning target, I can draw FBDs and solve problems for vertical circles. Reminders that when we're talking about circular motion, we don't actually have to do a full circle. Even part of a circle is still going to be considered circular motion. So that can be going around a curve, that can be going over a hill, as we mentioned, all sorts of different scenarios. With vertical circles, the circular view, that's where we draw out the centripetal force, the centripetal acceleration, and the velocity, and the free body diagram are typically both going to be able to be drawn from a side view, so that will hopefully make it easier to visualize and understand what is going on. A few reminders about the forces. Gravity. If we're on Earth, there's going to be gravity, and gravity is always going to be pointing down, as in toward the Earth. Normal force, remember that's going to be perpendicular to the surface, and that can be up, but it could also be down depending on if we're doing like a roller coaster loop. Here we're going to be talking about hills, so that's just going to be primarily up, although technically depending on where we are, it could be to the side. But in terms of, because we also have to talk about in towards the center of the circle and away from the center of the circle for circular motion, normal force could be either, as we'll see situations for both. And then finally, the centripetal force, reminder, is not its own force. Centripetal force means net force. Net force, we know, is never drawn on a free body diagram. So centripetal force will never be drawn on a free body diagram. But something we can keep in mind is that the centripetal force, centripetal means center seeking, is always going to be toward the center of the circle. So that means the net force for circular motion is always going to be inwards. So that will help us understand what's going on quite a bit. All right, so we're just gonna jump into some examples here. You'll definitely want some free body diagrams on these examples here. So hills part one, actually A doesn't even have hills in it. It's just a nice flat surface. And it says Amy drives a 12 meters per second along a flat road. Her mass is 70 kilograms. What is the normal force acting on her, as in Amy, right? Right. So to help us visualize this, as we mentioned, it's not even really a circle. So let's just kind of list out the information. 12 meters per second. The mass is 70 kilograms. Radius, there isn't any. Let's see, gravitational force is just going to equal mg as per usual, and we'll try to figure out what the normal force is. That's question mark. So the forces we have here, there's going to be gravitational force going downwards, and normal force is perpendicular to the surface, and that's going to be going upwards. That's the only two forces, and really looks like they're going to cancel out. So let's go ahead and draw out the net force equation. So when we're just talking about motion on the x or motion on the y, we say net force, in this case on the y, equals mass times acceleration on the y. And I've got normal minus grav is equal to, well, we're not accelerating on the y-axis, that's just going to be 0. So that means normal is equal to grav, which is equal to mg, which is, let's go ahead and tap that into our calculator. And that is going to be 686, and that's going to be newtons. All right, so that was actually really straightforward. That one is just the contrast, right? In this case, the normal is equal to the grav. That's not going to happen anymore. Oh, all right. Part B, Ben, who is also 70 kilograms, drives over a hill with a radius of 20 meters. So this is what we're looking at. This is a hill, And what we're talking about, if the hill is 20-meter radius. Remember, it doesn't have to be a perfect circle for us to be demonstrating circular motion. All right, so it's important that we understand from the side point of view, like, oh yeah, I can kind of trace out a circle on this road as we go over the hill. Okay, that's one of the big takeaways from here. Anyhow, we've got it says same speed, so that's going to be 12 meters per second, same mass, 70 kilograms. This time we do have a radius, that's going to be 20 meters. And gravitational force, well, if it's the same mass, it's the same weight, so it's going to be 686 newtons. So we say, oh, so is the normal force also? No, it is not actually. We are looking for the normal force. Let's go ahead and solve for that. So we, instead of saying the sum of the forces, because we are talking about motion in a circle, even if it's just part of a circle, so instead we're going to say centripetal force is equal to mass times centripetal acceleration. So okay, yeah, fine, that's fine. Okay, so what is the cause of the centripetal force? Oh, is it gravity? Is it normal? Well, actually, let's back it up a little bit. If we see we're going over the hill here, and let's see, we've got, this is the velocity here, and then we've got centripetal force is always inwards, that's the net force. Centripetal acceleration, this is the circular view, this is not the free body diagram. Let's draw the free body diagram down here. Okay, we've got gravity, which I'm trying to draw as the same gravity as up here in the orange. And then we've also got the normal force, but normal force is actually going to be smaller than before. So now how much smaller is it? It's tough to tell. I don't know at this moment. But normal force is going to be smaller, and let's go ahead and investigate why that is. We said that the centripetal force is going to be inwards, in towards the center. So that means the total, because the box is up on top, that means the total downward force is going to be larger than the total upward force. That will give us a net force or centripetal force inwards. So let's go ahead and list off the variables. When it comes to circular motion, as we mentioned, inwards is positive. Inwards is positive. So gravitational force is considered positive. The normal force is negative. So this is kind of different from what we're used to. We're used to saying up is positive and down is negative. For circular motion, we're going to say inwards is positive. So gravitational force is going inwards. If you want to visualize here as part of the circle here, we can say, oh yeah, gravitational force is definitely pointing towards the center. Normal is pointing away from the center, so that's considered negative because opposite direction. Equals mass velocity squared over r. You say, oh, okay, yeah, that's fine. Unfortunately, things don't equal zero and just cancel out and stuff. So we're going to solve for the normal force. So I'm going to leave grav where it is. I'm going to bring the centripetal force over, minus mv squared over r, and that's going to be equal to the normal force. Okay, so let's go ahead and, well, I guess we can just start plugging in. It's already rearranged for us. So I already know this is 686 newtons, and let's see, the mass is 70 kilograms. V is 12 meters per second. Don't forget the square. And the R is 20 meters. Okay, so that becomes, well, 686 newtons minus 504 newtons, which is going to equal 182 newtons, is the normal force. That is the normal force there. And you say, well, wait, is normal force going to be positive? Is it going to be negative? Remember, the free body diagram already took the whole directional thing into account. When we wrote out the equations, I had normal force as going upwards. I guess let's go ahead and indicate that downwards or kind of downwards for this perspective is positive. Okay, so that's why I have the positive sign for grav and negative sign for that. So we're really just finding out the size here. This is the magnitude of the normal force for this scenario, 182 newtons. Okay, that's the normal force acting on Ben. Okay, all right, that's fine. Now, something to keep in mind, as we mentioned, the gravitational force is going to be a constant size. The normal force is the part that's going to be changing. So normal force, as we mentioned, might be upwards, might be downwards, depends. Might be bigger, might be smaller. In this case, normal force is smaller, and hopefully that makes sense, because if you've ever gone over a hill kind of fast, you realize you're like, woo, like you're going over the hill, you feel a little bit lighter as you go over the hill. And if you recall from when we talked about elevators, as we are accelerating downwards, as you can see, this is accelerating toward the center. If we're accelerating downwards in the elevator, that's where we feel lighter. We're like, woo, as we're accelerating downwards. Okay, let's move on to more of these hills part 2. And we'll want to continue with these free body diagrams. All right, now part C, or question C, I guess part 2. Consuela, also at 70 kilograms, drives through a dip in the road with a radius of 20 meters. And this isn't really to scale here. This is, that's okay. 20 meters, same speed as before, 12 meters per second. So these numbers are really starting to sound familiar, right? Right. So we've got 12 meters per second. The mass is still going to be 70 kilograms. Radius, once again, 20 meters. If the circle is above the ground or below the ground, that's not really important for the radius. Radius is not a vector, so it's just going to still be 20. All right, and the gravitational force is same as before, because the mass is not changing and the acceleration due to gravity is not changing. So 686 newtons. And once again, we're looking for the normal force. Right. Okay, so let's go ahead and let's change up some colors. Let's go ahead and draw in. We've got, this is my velocity, and then we have centripetal force is inwards, so centripetal acceleration is inwards. So we'll draw the free body diagram over here, and we'll even draw the parts of the circle. That should be okay. We're not really drawing in any other forces or anything. It's just a reference. So as per usual, we've got gravity. That's supposed to be the same size as before. Doing my best there. And then we've got the normal force. Reminder that the centripetal force, which is the net force, is upwards. So that means the normal force is going to be larger than the gravitational force. Now, how much larger? That's tough to tell. We're just estimating here. But we do want to demonstrate that the upward force is larger than the downward force. So, okay, fine. And more colors. Let's go ahead and do the sum of the forces business. Remember that centripetal force equals mass times centripetal acceleration. We're treating inwards as positive. We can't simply say up or down as positive. Inwards is positive, so that means normal force minus grav, because grav is away from the center of the circle. Normal minus grav is equal to mv squared over r. So it's not simply we say, all right, we're back to normal where up is positive. We're saying up is positive because inwards is positive. You say, okay, fine. All right, so normal force minus grav is equal to mv squared over r. Once again, we're solving for normal force, so let's give ourselves plenty of space. Normal force equals mv squared over r plus gravitational force. Okay, you say, ooh, that normal force is going to be kind of big. Yes, it will be. And in fact, before we even solve the problem, we know that if we're going like from one hill to another and we're starting to go upwards, we know that we're going to feel heavier. It's more noticeable, say, like on a roller coaster when the when the portion of the circle is a little more obvious. But yeah, this is definitely going to be the case here. If we wanted to solve for the normal force, we can also look at it from the perspective of, if I factor out the m's, I'm just going to do this for a moment. That's going to be v squared over r, which is centripetal acceleration, plus g, because gravitational force is m times g, right? We're not going to, that's nothing really special about that, but we are seeing that the centripetal acceleration and the gravitational field, the acceleration due to gravity, are going to be working together. They're going to be increasing. So if we wanted to solve it for a bunch of different masses, we could try to set it up like this. But honestly, we'll just go back to the original setup, because we actually have a bunch of these values already. They're not changing, right? So normal force, that's the one that's changing, is equal to m times v squared over r. So once again, that's 70 kilograms. That's 12 meters per second. Gets squared. Divided by r, that's going to be 20 meters. Plus the gravitational force, which is 686 newtons. You don't even need a calculator on this because we've already done this, right? Okay. We know that this, that the centripetal force, or the net force, is 504. Now, instead of subtracting, we're just going to be adding 504 plus 686. Ooh, interesting. 504 newtons plus 686 newtons. That's the normal force. Oop. Normal force equals 1190 newtons. So the force on us is larger as we're going in this part here. I'm sorry, to clarify, the normal force is larger on us here, so we will feel heavier. Remember, normal force is going to be how heavy we feel in these situations, just like in an elevator. Our mass is not actually changing, though. Okay, that was Consuela, and now we have Danya, and guess what? 70 kilograms. Oh, what this weird coincidence. This just keeps on happening, right? Well, the point is to make a nice little comparison. But this time around, let's see. This time around, we're going to change up, not the velocity. That'll still be 12 meters per second, 70 kilograms. But we're going to change up the radius. The radius is only going to be 0.5 meters. And this is supposed to be similar to a speed hump or a speed bump. I don't really know the difference between those, but yeah, it's going to be 0.5 meters radius. So like from one end of the hump to the other would be a meter. So that's about 3 feet. So that's, yeah, it's easily something we'd be going over. That's not a very large one, but you do know, hopefully, that you want to slow down as you're coming up on those things, right? Because if you don't, that could be a problem. And that's exactly what we're going to be seeing here. 686 newtons. Let's see, we've got, this is the velocity. And as before, we've got centripetal force and the centripetal acceleration. Lovely, lovely, lovely. And that is our circular view. Let us go ahead and draw the free body diagram, and reminder that the curve is looking like that. And reminder, gravitational force is not changing. It's always downwards, and it's always the same value because we've been using 70 kilograms the whole time. So you say, okay, all right, let's see, normal force, is that going to be big or small? Reminder, the net force, centripetal force, is got to be inwards. Otherwise, we're not going to be doing a circle. So that means the total inward has to be larger than the total outwards, which means the normal force is going to be smaller. Okay. So let's go ahead and do our net force equation. Centripetal force equals mass times centripetal acceleration. And once again, gravitational is positive, right? So grav minus normal equals mass times centripetal acceleration. Now we're going to be solving for the normal as before. So, oh man, we already did this. I bet I already know the answer. Maybe v squared over r, I forgot to change that earlier, equals normal force. We know part of this. This is going to be 686 newtons. That's the weight the whole time, right? Minus 70 kilograms. V is still 12 meters per second. Some of you are like, hey, I'm so good at my math. I've got 12 meters per second squared. It's going to be 144 meters squared over second squared. That's cool. But remember the radius, is different now. 0.5 meters. And now that's going to be equal to the normal force. And now we're going to see a bit of a surprise. We have 686 newtons minus this guy right here, 70 times 144 divided by 0.5. Notice it's a number less than 1, so it's actually going to make the overall number larger. It's going to be 2160 newtons. Okay, so that's a huge, huge force there. It's a large force. And that's the centripetal force, right? In order to make this turn. Okay, so you say, this is kind of weird. All right, well, let's do the actual math. The actual math is going to say the normal force, 19,474 newtons, except there's a negative sign. I don't really know what that means. What's with the negative sign? Well, remember what we had said before. We're treating downwards as positive, and everything should be coming out as a positive value because we've already taken the negative signs into account, right? So what's with the negative sign? We already took the negative sign into account. So this negative sign does in fact have meaning. That means, well, frankly, what it means is we're going so fast, we're not able to do circular motion. This is essentially, instead of a speed bump, it has now become a ramp. Now, in the case of a car, what a car is like has a suspension system and stuff. That's not exactly rigid. So what would happen in reality is the car might actually get some air. Probably not. If this were a rigid object like a box or something like that going along at this speed, which is like 25 or more miles an hour, and it goes over this bump, that box would definitely catch some air. We would not actually be able to truly do circular motion because we would lose contact with the ground. Therefore, normal force is gone, and therefore it would really become a projectile. Okay, so crazy stuff. And also, if you think about it, you don't want to go too fast over these speed bumps, unless you want to become a projectile, which I don't think your car would really appreciate it. Thank you, physics, for helping us protect our cars. Physics. Oh, and I guess I should go back to the whole making sure that we have covered our learning target. I can draw free body diagrams and solve problems for vertical circles. Yuppers just did.